Welcome back to part 8 of the CISSP Exam Cram series. This is the big finish of the core lessons, and today we're covering Domain 8, Software Development Security. A short but important domain, so let's get right to it. And welcome back to Lesson 8 in the CISSP Exam Cram series. Today we're covering Domain 8, and if you haven't been through the first 7 of the core lessons in the series, by all means make sure you give each of those a look. And remember, we do have some supplemental videos that cover a number of important topics that will help you in your exam prep. So some of the key ones you need to have a look at include quantitative risk analysis formulas, hacking your CISSP exam prep, where I describe my preparation, and then of course the memorization tips. So all of these will help you get further faster. Couple that with the official CISSP exam study guide that I recommend, 1,300 questions, 700 flashcards, link in the video description. And Domain 8, which is Software Development Security, is another fairly short domain, but important. It has some topics that, if you're not a developer, you're maybe less likely to be all that familiar with. So you'll want to spend some time here on some core concepts. Let's have a look at the official exam outline. This comes from the ISC Squared website, and we'll see that in Domain 8 we are focused on software development security. So understanding the software development lifecycle, understanding security controls and how to identify and apply them, assessing the effectiveness of software security, the impact of security on acquired software, and then defining and applying secure coding guidelines and standards. There's some pretty interesting memorization that has to happen in here around some of these processes and frameworks. So let's start with Relational Database Management Systems. RDBMS is the acronym. You need to know the basic architecture of relational databases. So relational databases contain tables, sometimes called relations. A table will contain a number of fields, and each attribute corresponds to a column in the table. And I'll talk you through these, and then I'm going to show you an example which will lock this in for you. So rows are essentially data records. So one row of data is a record. So if it was a database of employees, I would be a record, you would be a record, that would be a row. And rows are sometimes called records, sometimes called tuples. Typically you're going to hear tables and rows when you're talking to people speaking in plain language, but it's a record. And then a column is a set of data values of a particular type. So a column in a record, for example, first name would be a column. Last name would be a column. Job title would be a column. These are sometimes called fields or attributes. And continuing down this row, with databases, I mentioned there's a table, right? So this is the table right here. That's the table. So it consists of the rows and the columns. So there's a row. That shouldn't surprise you there. And you'll notice that there's a company ID column there. That's probably a key, a primary key. We'll talk about keys in just a moment. And then there's a column. So let's talk about keys in the context of relational databases. So you have the concept of a candidate key. So a candidate key is composed of any set of attributes that can uniquely identify any record in a table. So no two records in the same table will ever contain the same value for all attributes that compose that key. So for example, first name and last name in an employee database would be pretty good until you have a second employee with the same name as the first person. If the moment there are two John Smiths, that's no longer a good key. That's where another column like employee ID could come in very handy to uniquely identify any record in that table. There can be one or more candidate keys per table. Now the primary key is selected from the set of candidate keys. There's only one of these per table. It's set by the designer, so it's chosen at design time. And then there are foreign keys. I'll need to show you just a quick example of this. Foreign keys are used to enforce relationships between two tables in a relational database. It enforces what's known as referential integrity. So it ensures that if one table contains a foreign key, it corresponds to a still existing primary key. So what do I mean by that? Let's just have a look. So I have here the picture of an e-commerce application. And this application is one that allows customers to give gifts to one another. So we can have customers giving gifts, but also receiving gifts. So in the customer table on the left, you'll see that we have a customer ID, right? That is the primary key of that table as noted by the PK. And over in the gift table, you'll notice there are two foreign keys. One of those is customer ID, the other is receiver ID. So there are two relationships between this table. There is the idea that a customer is the giver of the gift, and also the idea that a customer may be the receiver of the gift. So there is a primary key, foreign key relationship there between customer ID and then over in the gift table, either customer ID or receiver ID, since that can go in either direction as giver or receiver. So bottom line, if I were to try to delete a customer ID, the relational database management system should stop me because there is a relationship between these tables. I shouldn't be able to delete that record that contains that primary key that is referenced over in that other table where that foreign key relationship exists. So it enforces referential integrity. It's also going to prevent changes to the design of the database in a way that would break that referential integrity. So also, we'll want to talk about common relational database management threats. The two called out in the exam essentials are aggregation attacks and inference attacks. So let's have just a moment on these two. So aggregation attacks surround the ability to create sensitive information by combining non-sensitive data from separate sources. So finding seemingly benign data in multiple sources to then compile data that is then very sensitive. For example, maybe I add up a bunch of individual sales records to then create the total quarterly sales. Maybe quarterly sales is a number that's not released to the public, but as an employee, maybe I can go look at those individual records and add up those transactions to come up with that then sensitive data. Maybe I need to go to multiple databases to get that, multiple sources, but ultimately I can bring that together. Now, an inference attack is the ability to deduce or assume information by observing a non-sensitive piece of information. So the key there is a non-sensitive piece of information. So basically, aggregation involves multiple pieces of data. Inference is where we can deduce something based on a single piece of data. So these are certainly not the only two attacks a relational database management system is susceptible to, but they were given a special call out in the official CISSP study guide, so I wanted to bring your attention to those. RDBMS would be susceptible to other attacks like SQL injection, time of check, time of use, backdoor, denial of service, a wide variety that we've discussed earlier in the series for sure. Now you'll also be expected to be familiar with the various types of storage and their relative cost and performance on the exam. And by relative cost and performance, I mean less expensive, more expensive, faster, slower, volatile, non-volatile, etc. So not actual numbers or costs, just relative or comparative costs. So there's primary memory, which is your RAM that's available directly to the CPU. Volatile RAM, and we'll talk about volatile and non-volatile in a moment. But this is directly available to a system CPU. This is going to be the most high-performance storage available. And operations happening in memory are, generally speaking, always faster than operations that involve writing data out to a disk or storage of some sort. So secondary storage can consist of less expensive non-volatile storage. available for long-term use. This would be any sort of tape, disc, hard drive, magnetic or optical media, CD, DVD. There's virtual memory. Now this is interesting if you're not familiar with virtual memory and operating systems. This allows a system to simulate additional primary memory resources through the use of secondary storage. So for example, on a Windows system, you'll have a setting in the operating system that defines virtual memory by default. And if a system is low on real memory, on RAM, it can make hard disk space available for direct CPU addressing. So it creates a memory space on disk, so to speak. So it can flush data out of real memory to the disk so it can then work in memory. How virtual memory works exactly is not super important, but understand that virtual memory is when a system low on RAM makes disk available for direct CPU addressing. Moving on here, virtual storage. This allows a system to simulate secondary storage through the use of primary storage. So we said primary storage was RAM, right? That was the fastest, most high performance. Now if we're simulating secondary storage through the use of primary storage, we said secondary storage was your non-volatile media, right? So what happens in this case is what we call a RAM disk is a great example. So it provides a very fast file system for apps, but no recovery capability because it's simulating a disk. It's simulating disk storage in memory. But it allows us to perform a file system type operation very quickly. It just doesn't have recovery capability because it's sitting in volatile media. It's sitting in RAM. Random access storage just allows the operating system to request the contents from any point within the media. So RAM and hard drives are random access storage. Now, sequential access storage, on the other hand, requires scanning through the entire media from the beginning to reach a specific address. So a great example of this is magnetic tape. Backup tapes, perfect example of this, old school magnetic storage. I mentioned volatile and non-volatile, so let's just sort that out right quick. So volatile storage loses its content when power is removed from the resource. RAM that we talked about, primary storage, the most common example. When the system goes down, the contents of RAM are gone because it is volatile storage, which means that non-volatile storage, by comparison, does not depend upon the presence of power to maintain its content. So certainly magnetic, optical, and optical media and non-volatile RAM would be a couple of many examples. Now, really any storage you can imagine that doesn't lose its contents when it's not connected to power, that's a good example of non-volatile storage. So machine learning and neural networks. You'll be expected to have some fundamental knowledge here of a few terms. So let's start with expert systems. So expert systems consist of two main components. There's a knowledge base that contains a series of if-then type rules and an inference engine that uses that information to draw conclusions about other data. But essentially you have the knowledge base that contains vast numbers of records of information, and then you have the inference engine that evaluates that knowledge to draw conclusions. So machine learning, techniques that attempt to algorithmically discover knowledge from data sets, so using machine learning algorithms. And then neural networks. So neural networks simulate function of the human mind. They also require extensive training on a particular problem before they can offer solutions. I think those will be the two most distinct characteristics of a neural network. So know these three for the exam. Systems development. We're really talking about software development here. So there's Agile, which places emphasis on the needs of a customer and quickly developing and iterating in our solution. So basically rapidly creating new iterations or new versions of the eventual software product. So Agile is designed to be exactly that, agile, very responsive to customer needs. Now, Waterfall, on the other hand, describes a sequential development process that results in development of a finished product. So Waterfall is less responsive. I feel like Agile and Waterfall represent sort of opposing strategies. If you ask me to pick what's the opposite of Agile in terms of software development models, I would pick Waterfall. And we'll look at Waterfall in greater depth in just a moment. And then there's Spiral, which uses several iterations of the Waterfall model to produce a number of fully specified prototypes. So Spiral really addresses some of the problems that we see with Waterfall. In fact, let's just have a look at those right now. So we'll start with Agile. So Agile is a model for software development that's based on 4 principles. Individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. So the idea here is that we can produce a result that is more effective. It's closer to what the customer wants. It gets us to the finish line faster because we can pivot very quickly based on changes in requirements or changes in our understanding as we build the product and go through new experiences. For example, user experience testing may tell us that we need to pivot and change the way we're building software, and Agile is intended to be very responsive in that respect. So know those 4 principles: individuals and interactions over processes and tool, working software over documentation, collaboration over contracts, and responding to change over following the plan. Agile was actually first described in the Manifesto for Agile Software Development that was released back in 2001, and I really started seeing Agile back in the early 2000s, 2007 and beyond. All right, the waterfall model is a 7-stage process that allows a return to the previous stage for corrections. And to make sure that for the CISSP exam, you look at the 7-step waterfall model that is defined in the book. You will find versions of waterfall that out on the internet that tell you there are only 6 steps, but you see it goes from system requirements to software requirements to design to coding and debugging to testing and operations and maintenance. So the waterfall sort of visualized for you there. But waterfall, I mentioned, also allows a return to the previous phase from each phase. So each phase can only go back one phase for correction. So it's by design less flexible, less agile, if you will, than agile, pun intended. And then there's the spiral model. So the spiral model is a software development lifecycle model that allows for multiple iterations of a waterfall style process. So it's known as a meta model or a model of models. Each loop of the spiral you see on the right there results in the development of a new system prototype, a new iteration, if you will. So it provides a solution to the major criticism of the waterfall model. It allows developers to return to the planning stages as demands change. So in a word, it adds that property of iterative. It makes it more flexible. So it allows us to leverage a waterfall style process in a more customer-focused, responsive way, and allows us to iterate quickly through our product designs. So software development maturity models. These help software organizations improve maturity and quality of their software processes by implementing an evolutionary path from ad hoc development, chaotic processes where everybody is kind of on their own. They're not really following any sort of organized process or plan, and moving to a state of more mature, disciplined software processes. So for the CISSP exam, you will want to be familiar with the software capability maturity model, the SW-CMM, and the AGILE models. So, software capability maturity model. It's a 5-step model for measuring software development organization. So level 1 is no plan. Level 2 is implementation of a repeatable process, basic lifecycle management it's called. Level 3 is defined, where we have a documented software development process. Level 4 is managed. This is where we now have quantitative measures, meaning we can reliably measure performance to gain a detailed understanding of results and where improvements can be made. And then optimized, a continuous development process with feedback loops. This is the top of the mountain. I like to think of this in the world of DevOps. I would call this continuous integration, continuous deployment, continuous release it's sometimes called, but CI/CD. So this is where we have a high level of maturity and we can release software often and reliably. And then the AGILE model is a model for development that implements many of the software capability maturity model. So there's initiating, where our business reasons are outlined, support and infrastructure for the initiative are put in place. We have diagnosing, where engineers analyze the current state of the organization and make recommendation. We have establishing, where the organization takes those recommendations and they develop plans to achieve those changes. Acting, putting the plan into action. And learning, so the organization continuously analyzes their efforts and proposes new actions to drive better results. But notice that for each stage there, that's your acronym, AGILE. Initiating, diagnosing, establishing, acting, and learning. I think that's probably all the memory aids you need to remember AGILE. This was one of those that, since it was based on an acronym, I didn't actually create a memory device to try to remember it. I just remember and it's a very logical process, right? So let's talk about change and configuration management in the context of software development. So there's request control, which provides an organized framework. So users can request modifications and managers can look at those requests and basically perform a cost-benefit analysis. They can prioritize these tasks, prioritize the development backlog. Is the request reasonable? Is it affordable? Is it something many other customers want, for example? There's change control. This is used by developers to recreate the situation encountered and to analyze the changes to remedy the situation. And then there's release control. So once the changes are finalized, they can be approved for release through the release control procedure. So it should also include acceptance testing to ensure that the alterations were actually understood, they were developed as intended, as requested, and they are functional. So changes in this case really mean code changes that result in functionality changes in the software. Next up is software testing. So we have to test software thoroughly before we distribute that software. And the programming team, generally speaking, should develop special data sets that allow us to exercise all the paths of software navigation in an application to the fullest extent that's feasible. And some tests may be automated and others may be manual. So user experience testing, for example, that's typically going to be a manual test where a real person performs tests according to a plan and reports back their experience. They perform a task, they look at the actual result versus the expected result, for example. And many other types of tests may be automated. For example, if I want to test to see if fields in a web form are susceptible to buffer overflow, I basically need a way to replay input of a bunch of different values from a special data set to make sure that my application never throws an error, that it always responds as I expect. So that's something I could likely automate, unlike user experience testing. Virus propagation techniques. This is something that may come up on the exam, and there are 4 main propagation techniques you want to be familiar with. The first is file infection, which infects different types of executable files and trigger when the operating system attempts to execute them. So on a Windows system, for example, that's going to be .exe and .com files, generally speaking. There's a service injection attack, and service injection escapes detection by injecting themselves into trusted runtime processes in the OS. So on Windows, for example, that could be servicehost.exe, winlogon, or explorer.exe. Boot sector infection, which essentially just infects the legitimate boot sector, and it's loaded into memory during the operating system load process. So when you boot the system up or reboot the system. And then there's macro infection, which spread through code and macros like Visual Basic for apps in Microsoft Office docs. Antivirus software. So antivirus software comes in a couple of different flavors. So many in years past use signature-based detection algorithms to look for telltale patterns of known viruses, and many still use this. It is critical that signatures are updated frequently. For example, on the Windows platform is the best example I know to give you. We'll see multiple updates daily. Now, modern antivirus increasingly operate using behavior-based detection too, monitoring target systems for unusual activity and either blocking it or flagging it, even if it doesn't match a known malware signature. And modern antivirus often relies on some AI-driven or machine learning-driven intelligence, and some modern antivirus software will have a cloud connection where it can send off samples to get some input from a cloud-based system that can perform some additional analysis. And given that in the modern age, many threats are seen once and never again, they're unique, behavior-based detection is an absolute requirement. So the study guide mentions that it's increasingly common. Everybody's doing this. I'll just tell you right now. So techniques to compromise password security. You want to be familiar with all of these. So we have password crackers, which are designed to basically take credential data stolen in a breach and extract passwords from it. And the methods password crackers will use will vary widely. Dictionary attacks, these use a large dictionary file with thousands of words, and it basically runs an encryption function against all the words to obtain their encrypted, their hashed equivalents. But it's using existing words, whereas a brute force attack is when the attacker tries to attempt all possible combinations of a password to gain access to an account. So actually a dictionary attack is a type of brute force attack where the attacker, instead of trying to try all possible combinations, they try passwords from a dictionary file. Social engineering attacks. These consist of simply calling the user and asking for their password, or more often posing as a technical support representative or other authority figure who needs information immediately. You even see these carried out over the phone, where someone will call and say that they are from Microsoft support and they need your password, or they're from Apple support and you need to give them a password and you need to pay them some amount of money to help you. These are attacks that sometimes feel very realistic. I do remember once I was actually traveling internationally and I was on my way back home, and someone called me while I was in an airport lounge and said, "Hey, I'm on the phone with Apple support. They're asking me to buy these gift cards to pay them for support because there's a breach on my iPad." Completely social engineering attack. That sort of demand is never going to come from Microsoft or Apple or any legitimate company, and I was thankfully for them able to advise them and to stop that. So social engineering is powerful. A way to stop social engineering is through security awareness training. Number one countermeasure. Rootkit. Rootkit is a piece of software freely available on the internet. It's used as a second step by attackers to exploit known vulnerabilities to enable attackers to elevate or escalate their privilege, to gain greater privilege on the system once they have established residence. So let's touch on application attacks, which are used by attackers to go after poorly written software, to exploit poorly written software. The most common you'll likely hear about is the buffer overflow, where a developer does not validate user input to ensure that it's of an appropriate size. This is really common in web forms. And if the form doesn't validate the input, the user can potentially input data that is too large, and it can overflow the memory buffer, causing an error, a buffer overflow error. There's a backdoor. This is an undocumented command sequence or sequences that allow individuals with knowledge of the backdoor to bypass normal access restrictions, often used during development and debugging, and in the worst cases, unintentionally or even intentionally left there after development and debugging. There's time of check to time of use attacks, which is a timing vulnerability that occurs when a program checks access permissions too far in advance of a resource request. So it's a timing issue. And rootkit, which is escalation of privilege. So rootkits are freely available on the internet, and they're intended to exploit known vulnerabilities in various operating systems, enabling attackers to elevate privilege. So you'd see this in an escalation of privilege attack scenario. Web application vulnerabilities. There are two very common web app vulnerabilities you want to be aware of, and you'll find that there are vulnerabilities that compromise front-end web interfaces or web systems and back-end databases, and sometimes they're using the front end to compromise or access the back end. So there is the cross-site scripting, which is a type of injection attack in which malicious scripts are injected into or otherwise benign and trusted websites. So these occur when an attacker uses a web application to send malicious code to a different end user. They occur when web apps contain reflected input. For example, I put my name into a field on a form, I hit submit, and it says, "Hello, Pete." SQL injection attack. So these use unexpected input into a web application, into a front end, to gain unauthorized access to an underlying database. There are quite a few different ways I've seen SQL injection attacks play out. I saw one of these in real time a few years ago, where a pen tester was able to put unexpected input into a web form, and it caused the database, caused the code to return information from the database you'd never want exposed. Next up are reconnaissance techniques. So these are techniques used by attackers who are preparing to attack a network. So this is data collection and learning ahead of the attack. So IP probes, automated tools basically pinging each IP address in a range, so performing a ping sweep, and then systems that respond to the ping request are basically logged for further analysis in the next step. So then you'll commonly see a port scan, which will look for open or listening ports on a system. So for example, ports 80 and 443 would be indicative of a web server. Port 445, TCP 445 would be a file server. So looking for servers supporting critical operations and services are going to be prime targets. And then you have vulnerability scanners that can be used to scan for specific vulnerabilities in a system. So a few popular tools out there include Nessus, OpenVAS, Qualys, Core Impact, quite a few vulnerability scanners on the market today. I don't think you'll be tested on your knowledge of vulnerability scanner brands, but I wanted to throw a few out there, which incidentally are also mentioned in the book, I believe, in the official study guide, by the by. So protection rings may come up. These are used to protect data and functionality from faults. You'll hear about these in operating systems. So for example, ring 0 is kernel mode, ring 1 and 2 would be device drivers, ring 3 are applications. And then within the system there are special call gates between the rings that are defined to allow the outer rings to gain access to the inner rings through predefined mechanisms rather than just arbitrary access. The software development lifecycle. You want to be familiar with the 5 phases of the software development lifecycle. So phase 1, requirements analysis, phase 2, design, phase 3, implementation, phase 4, testing, and phase 5, evolution. I have for you here a memory device to help you lock these 5 phases in to your mind. Real developers' ideas take effort. So I came up with this memory device because I wanted something that was relevant to the subject at hand, which is software development, but also followed the first letter of each of the phases of the software development lifecycle. So requirements, design, implementation, testing, and evolution. Real developers' ideas take effort. If you want a memory device, there you have it. Concentric circle security. So if you've spent any time in cybersecurity, you are familiar with concentric circle security, although you've probably never heard it referred to as concentric circle security. That is a very theoretical phrase that doesn't come up in the real world very often. So this security model consists of several mutually independent security applications, processes, or services that operate toward a single common goal. So it avoids a monolithic security stance by having multiple independent applications, tools, and processes working together to provide better security. So basically, every individual security mechanism has a flaw or a workaround, and we have to bear that in mind. And by combining intelligent combinations of countermeasures into what we call a layered defense, we can provide significant resistance to persistent attempts to compromise our network. This is called a layered defense. You'll also hear this referred to as defense in depth. So you want to be familiar with concentric circle security, but tie this to layered defense, defense in depth, and avoiding a monolithic security stance. And finally, the security impact of acquired software. So 4 categories here. There's operating system attacks. So attackers are always looking for vulnerabilities in an operating system, buffer overflows, other bugs, systems that simply haven't been patched in a long period of time, or patched for specific vulnerabilities. There are application level attacks. We've talked about a few of these: SQL injection, cross-site scripting, denial of service, hijacking, phishing, which is an email-based application level attack. There are shrink wrap code attacks. So these are exploiting holes in unpatched or poorly configured software you buy and install. A lot of times, software you buy and install will contain sample scripts or code, and those will be exploited if an attacker can find them. Then finally, misconfiguration attacks, which target poorly configured services or devices, or one that's left in a default configuration. A Wi-Fi router left in the default settings is a fabulous example. I can remember back in the day, Netgear routers came with a very simple admin username and password, and it was really common that folks would buy that Netgear router, take it home, and not really change anything about it, meaning that if one could connect to, say, the default Wi-Fi network defined on a Netgear router, if the user had left the default Wi-Fi network name, the default SSID, then chances are they probably left the default credentials on the device as well. And so that's a misconfiguration attack. And congratulations, you've reached the end of Domain 8, Module 8, the last of the core modules in the CISSP Exam Cram series. If you have any questions as you continue down the road of exam preparation, leave me a comment in one of the video comment sections. Come find me on LinkedIn or social media. Happy to help in any way I can. Make sure you get a copy of that official CISSP Exam Cram guide and spend some time with those questions and flashcards. And watch out for future supplemental videos in this series. I've already provided a few and I will provide more. And until next time, be well and stay safe.